Hello everyone, I'm Chika Yoshimura and he is Takeshi Tomochika. We are working at NTT Communications in Japan. Our company is providing internet services globally and also operates an ISP in Japan. We are designers of the backbone network of the ISP, which is called OCN, Open Computer Network. Internet traffic and free routes have been growing more and more. No matter how much traffic and routes grow, we have to carry the traffic with stability and without any congestion. This is our first mission. To do that, we have to make our backbone robust. Today, we'll be talking about the current traffic situation in Japan, and some issues when designing the backbone network and future visions. The Japanese government estimates the total amount of traffic of broadband users in Japan and announces it semi-annually. Here is a graph showing the total traffic from 2004 to 2010. Red line is the average amount of download traffic, which means from ISP to users. It has been rising and reached 1.7 terabps in 2010. Compared with last year, it increased by 25.4%. The Japanese government did not mention what kind of traffic is growing specifically, but we guess that HTTP streaming like YouTube and CDN traffic like Akamai and Limelight are driving up the traffic. Blue one is the average of upload traffic, which means from users to ISPs. It reached 896 gigabps in 2010 and decreased over the last year. In Japan, the copyright law was revised in early 2010. It became illegal to download files when knowing the files are illegal. We guess that it led to the decrease of upload traffic, especially P2P traffic. Traffic volume per subscribers has also been growing. It was 50 kilobps in 2010. The broadband environment already has been established in Japan. There are over 30 million subscribers who use cable TV, DSL, and FTTH. Especially, they have shifted from DSL to FTTH. As you know, the number of full routes has been growing. The number of IPv4 prefixes is over 330,000 in June 2011, and IPv6 is around 6,000. Anyway, internet traffic and full routes have been growing consistently. This is a very difficult situation for ISPs because we have to try to keep backbone robust, dealing with these two issues. Next, I will introduce the backbone we've been making and the bandwidth we have specifically. This map indicates our backbone network. We have two ASs. The upper one is NTT.NET, which AS number is 29410. The lower is today's forecast OCN, which AS number is 4713. In OCN, there are 4 POPs where core routers are placed. These are Gunma and Tokyo in eastern Japan, and Aichi and Osaka in the rest of Japan. A core router in the east is connected to another core router in the west. The bandwidth between them is 400 gigabps in total. On the other hand, gateway routers Sorry to interrupt. On the other hand, the gateway routers connected to the internet, which means NTT.net for us, are placed in Tokyo and Osaka. The traffic from OCN to overseas is carried by NTT.net. The bandwidth between them is 860 gigabps. The traffic to other ISPs within Japan passes through IX and private peers, but I will leave out the fine details today. The regional POPs are placed around the location of core routers. There are 12 regional POPs in cities all over Japan, and each edge router in the POPs is connected to 2 core routers. There are 3 features of our backbone. First is that there are no single points of failure. Every regional POP has 2 circuits, 2 core routers, and every router in the backbone has redundant routing engines. Second is that we have double bandwidth of the peak traffic for every line. Even when the path goes down during peak traffic hours, the other path can handle all the traffic. Third is disaster tolerance. It is more than 100 kilometer distance between core POPs to avoid the impact of the disasters. When the disaster happens in Tokyo, the core router in Tokyo may go down, but our customers in eastern Japan, except Tokyo, like Hokkaido and Tohoku, would be able to use the internet because a core router in Gunma is still alive. We have a lot of design issues in our backbone, but today I would like to introduce 2 issues. First is scalability of router forwarding tables to cope with increasing routes. Second is about link aggregation to handle the traffic. Fib table has been growing. Inside our backbone, the number of routes of IPv4 was around 360,000 in 2009 and is more than 410,000 right now. Fib growth arises from some causes. One of these is the growth of internet full routes and also the growth of prefixes which are used internally with no export BGP community. The number of prefixes with no export is around several tens of thousands in our backbone. When a rerouting event occurs, potentially thousands of routes must be updated. There are 4 routers, router A, B, C, and D. Interface 4 and 5 are aggregated as interface 3 between router A and D. Router A has 3 paths to reach to 10.1/16 and 10.2/16. If interface 4 goes down, router A must update 2 routes to erase the information of interface 4. When some member links of a link aggregation were taken down, a certain router in OCN took a lot of time to converge the routes. When the router has 360,000 routes, it took more than 130 seconds. When 500,000 routes, more than 210 seconds. The convergence time increases in proportion to the number of routes. We faced a problem that OSPF neighbor went down during Fib convergence. Here are router A and B. Between them, link aggregation had been enabled. Minimum link was 1. OSPF neighbor had been connected through the WAG interface. When all member links but 1 had been disabled in router B, we had expected that OSPF neighbor remained up because one interface was still alive. OSPF hello packets should be exchanged over the interface. Actually, what happened is here. OSPF hellos were exchanged over this member link firstly, and some links including this were made disabled in router B. Then router A detected it and started updating fib to wipe out the information of the links. Router A finished updating it. After this, router A chose another interface, which is still alive, to send hellos. During 1, 2, and 3, router A could not send any hellos because of not changing over the interface. It took more than 40 seconds, which is OSPF dead timer. This trouble arises in case of using flattened fib. So we started to use hierarchical fib. This is too difficult to pronounce for me. Hierarchical fib, like BGP PIC of Cisco and indirect next hop Juniper of Juniper. Then the convergence time was very improved. It was shortened from more than 210 seconds to around 25 seconds. For more information about hierarchical fib, please see this link presented by Cisco at NANOG 40. And I'm passing the baton to Tomochika-san, and he will explain the second issue.
I'm sorry, the screen somehow lack the edge of screen. So I change the PC. Here is my where?
Yep.
Oh, this one. 違うの。どうやるんだこれ。あ、これか。あったあった。Okay.
Why it's not on the screen?
Not yet.
So I closed it and reopened it, but it's not on.
This one.
Did you do a function 8?
Should we press any button?
Function 8.
Function.
I can't see it.
Duplicate. This one.
There we go.
We are very sorry that. Hello everyone, I'm Takeshi Tomochika, Network Engineering Manager of OCN, coming from Japan. Today, it's very honor for me to have give a presentation in NANOG meeting. So I'm talking about link aggregation issues and our future plan. Okay, let's move on. This slide shows bandwidth history of OCN. As you can see, bandwidth of OCN has been growing like exponentially. And this is our backbone map. As you can see, we have a lot of links over 100 gigabps. So we have a large number of 10 giga ether interface. Actually, more than 1,010 giga ether interfaces. So we are using a lot of link aggregation 10 giga ether interfaces in our backbone. This slide shows what I will talk about. First, I will talk about traffic load balancing issue, so-called traffic polarization, including 3 cases, and then I'll explain operation considerations and other issues. From now on, I'm going to talk about traffic load balancing issues, but first of all, there is a condition of traffic load balancing method in the RAG, which is we cannot use per packet round robin, because simple round robin brings about packet reordering in a flow, which might have a bad influence to end users. So we and maybe many ISPs, most of ISPs should use flow-based traffic load balancing method. Normally, hash value is used for flow-based traffic load balance. Hash algorithm calculates the hash value based on the packet information, such as IP addresses and MAC addresses. This figure shows. So, due to limited time, I skip this slide because this is a very small issue. And then this is a bigger issue. Issue number 2, limited number of hash elements. Due to this, traffic cannot be evenly distributed, which causes less effective use of bandwidth. In addition, the less number of hash elements, the worse traffic balance. For example, this slide shows traffic balance in a lag when the number of hash elements is 8. So please focus on the case of 5-link 10 gigaether lag. In this case, okay, two hash values can be assigned at each of interface 1, 2, and 3, while only one hash value can be assigned at each of interface 4 and 5. In order to avoid packet loss at interface number 1, 2, 3, each hash value can deal with only 5 gigabps. As a result, interface 4 and internet 5 can use only 5 gigabps, even though they are 10 gigaether interfaces. So totally, we can use only 40 gigabps out of 50 gigabps, which is 5-link 10 gigaether lag. So this slide shows the difference in traffic balance by the number of hash elements. As can be seen, the more number of hash elements, the better traffic balance. But even when the number of hash elements is 32, we can use only 45.7 gigabps out of 50 gigabps. So typically, we should avoid the odd number of member links in a lag. Okay, now I'm going to introduce issue number 3, combination of ECMPs, equal quota multipass, and lags. Case number 1, when hash calculation logic of lag is the same as ECMPs, it will bring about unbalanced traffic in physical links. Let me explain by using this slide, this figure. So suppose that there are flow 1, 2, 3, 4, which are coming to node 1, and node 1 makes hash calculation for ECMP, like that. And then suppose that flow number 1 and number 2 go to upper side of this figure, lag 1, and then flow number 3 and number 4 go to lower side of this figure, lag 2. And if hash calculation for lag at node 1 has the same logic as hash calculation for ECMP has, both flow 1 and 2 go to physical link number 1, upper side of physical link in lag 1. Because both flow 1 and flow 2 have characters to go upper side of this figure. So as a result, and actually, all of the traffic going through lag 1 goes through physical link number 1. So it brings about no traffic in physical link number 2 and lead to unbalance in lag 1. And similarly, all of the traffic going through lag 2 goes through physical link number 4, this figure shows. So we have to be careful to avoid this, because some routers have the same calculation logics for ECMP and lag as a default. So you might think, okay, I've understood. So I'll change hash calculation for lag at node 1. It must be enough, but actually it's not enough. When calculation logic of ECMP is the same as that of next node, it will bring about unbalanced traffic too, like this. So we need to pay attention not only node 1, but also node 2. So maybe the one say, okay, I've totally understood, so I change hash calculation for ECMP at node 2. It must be enough. But actually, no, it's not enough. Even when you change hash calculation for ECMP at node 2, when calculation logic of ECMP is the same as that of lag at the next node, it will bring about unbalanced traffic in this way. Actually, some latest routers can include a router ID in the seed of hash to avoid case number 2 and 3. But since we have not only latest routers, but also relatively old routers, so, and in actual network, there are a lot of flows, not only left side to right side, and also, but also right to right side, or right to right side, or upper side to right downside, many flows. So we need to consider load balance logic, network topology, and configurations. So from now on, I'm going to talk about operational considerations, but due to limited time, I skip this slide. What I wanted to talk about in this slide is please pay attention to detailed interoperability of LSCP. And then this is also I skipped this slide. What I wanted to talk about in this slide is ISP should consider the entire network topology to use minimum links. Oh, this animation shows what minimum links is. Okay, number 3, ping. By ping, packet goes through only one physical interfaces. So we need to test each interface with letting the rest go down. Actually, it's very troublesome job. But some recent routers and switches support Ether OM to avoid this troublesome job. But you know, since we have not only latest routers, so we are doing this troublesome job still. Please imagine that there are 16 physical links in a lag. It's very troublesome. And finally, this is other issues. First of all, there are limitations on the number of links in a lag. 16 is not enough for us actually now. And second, there are issues of physical wiring by increased number of physical links, which brings about complicated maintenance. Please imagine that your facility is like that. Oh, please keep in mind, this is not our equipment. Okay. Third, we need a well thought out plan for lag. So when we decide how to assign physical links to line cards, we need to consider and think over a redundant policy and MTBA for each part and the cost, and etc. Actually, there are a lot of policies we can choose, but we need to consider a lot to use lag. So the conclusion is that lag is very troublesome, especially when we are using many lags and many member links exist in a lag. Okay, I'm going to talk about our future plan quickly. So this is our OCN backbone. About 4 years later. Okay, you can see we will have some links over 1 terabps. So we need 100 gigabps interfaces because of bandwidth over 1 terabps and lag is troublesome. So our request is that first of all, lower price. CFP is very expensive still, and I think 10 by 10 MSA, the former LR10, is inexpensive, and but I think not all router vendors support 10 by 10 MSA. But if this 10 by 10 MSA is inexpensive and stable and quality is good, please, and I want many vendors to support this 10 by 10 MSA. And also, we want long-distance transmission such as ER4 because we have a lot of dark fibers in our metropolitan area. And we need higher capacity. In some current routers, actually, capacity per chassis will be decreased when migrating from 10 giga ether to 100 giga ethers, which makes us very difficult to install 100 giga BPS. And if possible, we want lag of 10 giga ether and 100 giga ether simultaneously. And also, we need good interoperability, of course, easy operation 100 giga lag, and convenient ether OAM. And finally, we want many vendors to step forward to 400 giga ether and 1 tera ether. Okay, this slide introduces 100 giga ether joint interoperative test at JPNAP. JPNAP coordinated it, and Brocade, Cisco, Juniper as a router vendor, and your corporation as a vendor of Spirent, and JPNAP as a IX provider, and IIJ and Entity Communications, OCN as an ISP, took part in this test. We succeeded in 100 gigabit Ethernet joint interoperability test at IX, and we confirmed that the interoperability between different vendors' products, especially at an IX environment. Actually, they have good interoperability, much better than we expected. But there are small issues with each product, so we made feedback to our router vendors with some requests. For example, we want to monitor more about layer 1 status because 100 giga ether is using WDM technologies. But I cannot talk about it in detail because of LDA, so you can see further information at this URL. And if possible, in next NANOG, we could share this information in detail with participants. Okay, finally, this is a summary of our presentation. The traffic in Japan and BGP table has been consistently growing. We need to consider growth of both routes and traffic to keep our backbone stable, and lag is troublesome, and we need 100 giga ether to deal with the traffic growth. So thank you very much. This is the end of my presentation.
Thank you very much. Unfortunately, we're going to run short on time, so we won't have time for questions. But thank you for your presentation.